Okay, so we are going to continue our discussion from last time. We were talking about remote procedure calls or RPCs. Okay, so, and RPCs are essentially a way by which one process can invoke a function or a method in another process. So the code for, so when you invoke a function, the code for this function is not in this process, it's somewhere else. So you have to send a message to this other process saying, execute this method, here are the parameters. So the process executes the method and sends back a reply message. Okay? So this happens over the network. And I said RPCs are a fundamental primitive to write distributed applications of all sorts. Okay? So when you have client-server system or peer-to-peer system, many of them use RPCs for communication. Okay? So you send requests. The requests are essentially method invocations or procedure calls in another process. You execute the method and you return back results. Okay, so that's how RPCs work. So what we are going to do today is talk about distributed file systems. So there's two reasons for it. One is it's an example distributed application, a client-server application. It's a file-server application, but nevertheless it's a client-server application. So this allows us to look at how distributed systems and distributed applications are built. That's the first thing. The second thing is distributed file systems are also implemented using remote procedure calls, as we will see. So the other thing that we get out of this topic is understand how RPCs are used to implement a system like this. And so it's an example of an application, client-server application, and one that uses RPC. So we'll actually get a flavor of both. So I presume you have some idea of what a distributed file system, also called a network file system, is. Okay, so this is basically the ability for one machine to access files that are stored on a disk on a different machine. Okay? Typically, when you have your laptop, all the files are stored on your local disk. Okay, so all the file accesses go to your local disk. Okay? Now consider a scenario where you have another machine that has files and you want to access those files from a second machine, let's say your laptop. Okay? The way you would make this work is the machine where the files reside has to become a server and it has to accept requests for files from clients, and clients will send requests, access those files, modify them, create new files and so on. Okay? So this allows you to extend the functionality of a file system to remote machines, and that is what a distributed file system does. Okay, so the basic idea is given a set of disks or some storage that's attached to machines, you want to be able to share these disks. Okay, so the first thing is you're sharing the disks across machines. Okay, you're sharing file systems, files, disks, and storage across machines. Okay, so you want to enable the sharing, and from a client's perspective, it should look like you're accessing these files as if they were local. It shouldn't actually matter whether the files are stored on a local disk or a remote disk. For our application, it should look like it's accessing local files, even though the files are actually remote. So the abstraction is still the same. You get our ability to access files, except that underneath, the files are actually being accessed from a remote machine. Okay? Now, there are many examples where this is true. You probably have used network drives or network volumes on machines. If you have encountered a distributed file system of some sort, and you look at several examples in Mac, Windows, and the Linux world as well. Okay? And if you have actually used the EdLab uses a file system called NFS, Network File System, that provides the same functionality. There are EdLab servers. This is where the home directories reside. This is where the course directories reside, and so on. And then there are EdLab workstations. These are client machines. So when you log into a workstation, your file home directory, which is actually on a remote machine, is made accessible to you on that workstation. Okay? So it looks like your home directory is local, even though it actually resides on a remote machine or a remote server. And that is enabled through the mechanism of a distributed file system. Okay? If you use Mac, you have Apple Share or Apple File Protocol, AFP, that allows you to do the same thing. In Windows, you have network drives. In Unix and Linux, you have NFS, as we will see in more detail, the same mechanism that's used in the EdLab. Okay, so there are many different issues to consider when you design a file system, and we look at a couple of this in more detail, not all of them, because this is advanced material from a graduate course, so I only do a stripped down version of what we studied there. Okay? So those are the issues you have to consider. The first one is file naming, and this is basically the problem of how do you actually access a file? What is the name of a remote file? How do you decide what server it belongs to? How do you address it, and so on? Okay? So that's called naming. Okay? Remote file access relates to how the file system implements remote file access. Okay? You'll see there are two mechanisms to do this. And one is to actually send all of the requests over to the server. The other one is to have the server send data. If you remember last time I was talking about migrating computational data, which is the requests go to where the data is, or the data comes to where the requests are. Okay? The file servers, or sort of distributed file servers, employ both of these models. Some of them send requests where the data is, others bring the data, which is files, to where the requests are being made. Okay? So both of those models are prevalent, and that's the remote file access. Caching is used to optimize the performance when you send requests to a remote machine. The disk looks even slower than usual. Your disk is an I/O device that's already slow. If the disk is remote, to access it, you have to first send the message over a network. That takes some overhead, and then you have to make a local I/O on that disk. Okay, so now the remote disk accesses are going to be even slower than local disk accesses. So how do you improve performance? You actually employ caching to do that. Okay, so we'll look at a little bit of that. And the last two topics we'll touch upon very briefly. Okay, these have to do with whether the file server maintains state or what clients are accessing it, or whether it's stateless, and whether you can replicate files on multiple machines for better performance. Okay. The first three topics is what we will actually look at. The last two touch upon briefly. Okay, so let us start with the problem of naming and transparency. So the issues here are how are remote files named? Okay. Do the file names reveal the location, what servers they are on? What happens to the file name if the file moves, okay, or the user moves to a different machine, and so on? Okay. And there are two broad principles here that will answer all of those questions. Okay. That's called location transparency and location independence. Okay. Location transparency says that the name of the file does not reveal its location. Okay. So when you have a location transparent distributed file system, file names look like local names, remote file names look like local file names. So you may have, let's say, a file that looks like this. So it just says /home/user /project1.cc. That's the name of your file. That's how you're going to actually access that file. Now, if you look at this file name, it doesn't, just by the file name, you cannot tell whether this file is stored on a local disk or a remote disk. Right? It's just showing you a directory and some path. That by itself is not going to reveal anything to you. Okay, if you use a naming convention like this, you have location transparency. Okay? In fact, if you go to the end lab, this is the naming convention that is used. And these files that you are accessing from the end lab workstations are actually remote files, because this entire directory, your home directory, is stored on a remote file server. But when you, the user, or your applications access this file, all of this is hidden from you. Okay? This is happening underneath. You are not actually even aware that the files are stored remotely, unless you go and look at where the file is, where the volume resides, and so on. Just from the file name, you cannot tell. Okay? So this is an example of a naming convention that is location transparent. Okay, I'm going to give you another example. Okay, so let's take the web, okay, which is not a file system, but just for simplicity, you all know how web URLs work. So if you look at a typical URL, so you have something like www.cs.umass.edu/index.html. Okay? That's a naming convention that allows you to get to a file called index.html. Okay? It's not a file system, but it's the web, but it still uses a naming convention. And the observation here is this name is not location transparent. It actually embeds the name of the server within the name. Okay? So you have to first give the name of the server, where the file resides and then a path on that server. Okay? And there are windows as a naming convention that looks somewhat similar. If you actually use Windows Network Share, you have // a server name, then you basically have some path saying let's say users. So you will have a name like that, which is // server name and then / and a path on that server. Okay? That's an example of a file name that's not location transparent, because you have to specify the name of the server and the file resides in order to get to it. Okay? So you will see now there are two ways to do this. One is you will make file names look like local files, okay? And the OS underneath is taking care of mapping these files to a server. Okay? The OS figures out which server this file resides on, because there are mappings that are set up at boot time or configuration time. So user doesn't have to deal with it. The second one is more explicit, where the user actually has to specify on the access of file what server the file resides on, and then what path on that server the file is at. Okay? So the OS simply takes that entire name and sends the request to that server and accesses the file. Okay? So two different ways of naming files within distributed file system. One is location transparent and the other one is not location transparent. Okay? So that's the first concept. Now the second concept is called location independence, which says that the name of the file does not change if the location, the storage location of the file changes. Okay? Which means that the name of the file is not tied to its location. Clearly, if you are not location transparent, you cannot be location independent, because the name of the file actually has the location in it. So if you move that file to a different server, you have to now give a different path name to access the file. You have to say // new server name. Or if you move the web server or the website, this website to a different server, the prefix of the URL will have to change to the new web server. Okay? So if you're not location transparent, you cannot be location independent at all. But if you're location transparent, then whether you're location independent or not depends on the file system. Because in this scenario, okay, where the home directories are addressed this way, okay, if you move the entire home directory on a new server, the path name does not need to change if underneath you change the mappings. OS can actually take care of it. Okay? And in certain file systems, you have handles that are independent of this server itself. Even if you change it, you don't even have to change the configuration. The file handle tells you where to go and look for the file. The file handle is basically the entire path name to that file. It reveals, it does not embed the location is determined automatically. Okay? So location independence is the other concept. Most file systems that you will encounter will try to provide location transparency, because it's a convenience that the users can actually take advantage of. You don't have to remember this name of the server where your files reside. It is dealt for you by the OS. Okay? Location independence is a concept that relatively few file systems will implement. If you actually move the file to a different server, you will have to change at least the configuration, if not the path name itself, to access the file. Okay? Is that clear? Straightforward concept of how file names are used in a distributed file system. There's the issue of transparency and independence. Okay? So with that, let's now take a look at a few file systems that actually exist out there and look at how they deal with network files and so on. Okay? So the first naming convention is what is referred to as absolute path names. Okay, this is what is used in Windows. That's an example of what I showed you here, where you have to say, to access a file, you have to give the machine name and a path name on that machine. So an absolute name, it gives you all the information you need to know to figure out where the file is. There's the name of a machine that the file resides on, and the full path name of that machine. Okay. So as I said, Windows uses this, Apple uses this in some shape or form as well. Okay? And I'm going to show you an example of how to do this in Apple, but let's look at the advantages and disadvantages. So first of all, this is a fully specified file name. Okay? So this puts burden on the users to actually give you all of the information, you meaning the OS, and then the OS doesn't have to do much at all. So in that sense, it's simple. There is no global state. No one doesn't have to maintain any extra information to figure out where the files are and so on. And it's going to scale because there is very little burden on the OS. Okay? The disadvantage is all from a user perspective, which is the users now need to specify always the name of the volume when they access files. The file is location dependent. If you move it, the file name has to change. It's going to make sharing harder because you have to now specify file names and so on. Okay? So that's basically the simplest naming strategy, which is absolute file names. And if you have ever used any, I'm going to show you an example. So if you actually go to so in Apple you go and say AFP is Apple File Protocol, you give the name of the server. In this case it's going to ask me to authenticate, which I will. And then it's giving me some options of what volumes I can mount. I'm going to mount one of them. And now I have created a network drive where I'm accessing, in this case, my home directory on our group file server. Okay, so that's basically that home directory. I just created a network name which included the file name, and then it gave me a volume. I said go mount my home directory, and it mounted my home directory, and then it creates a network volume. Okay, there now. So these are all files now that I can access on my file server. Once I've created this mapping, they just look like local files. So if you go to a terminal, go to terminal window, and so it is mounted. So I can just go into that directory, I can look up my files and so on. Okay, so they just look like local files because I created this network drive. Okay. Now, but the important thing to keep in mind in this very simple example is to set up the network volume and to set up a file server. And I could have given a path on the server. If I did not specify a path, the system prompts me saying what volume do you want to mount in this specified path. But I could have given a full path that said server name / and then do my home directory, and it would then mount my home directory. Same thing you have to do in Windows. Okay, if you create a network drive, an E drive or an F drive, you basically specify a server name and a volume. Okay? So these are called absolute file names, or absolute names. Any questions on this? Okay, so the next strategy is what is used in the Unix world, and this is called mount points. Okay? So in this case, the system administrator sets up at boot time a mapping between file servers and certain directories on that file servers, and a mount point, a point on the local file hierarchy where those files become accessible. Okay? And there is a protocol called the mount protocol that is run at boot time. You can also run it after the machine boot, but it will run by default at boot time to set up those mappings. And then I'm going to show you an example of how this is going to work. Okay, so let's take the EndLab example. Okay, so in the EndLab you have your EndLab server. Okay, so this has home directories, okay, which is where all your file resides. It has course directories. Okay, so the root directory, and let's say you have the directory courses. Within courses you have CS300, which is all 300 level courses, and then you have 377. Okay. So that is where all the course specific files of this course reside. Okay, if you use the EndLab system. Okay. Now you have, in this case, let's say EndLab workstation, and let's say you now SSH into that machine. Okay. You need access to both your home directory and this course directory. How is that set up in the Unix world or the Linux world? What happens is the file server, when it boots up, will export certain volumes. Okay. Exporting is the process of telling other clients that they can actually access those files. Okay. By default, you can't go and access an arbitrary file on the file server. The file server has to be willing, Okay, or the system administrator or the user to control the file servers have to be willing to let other machines access it. Okay? The way you do this is you specify to the OS on the file server saying these files can be accessed remotely. So what you will do is you will actually go and run an export on this part of the file. You can say /courses. Okay? Anything in that volume can be accessed by some other machine. Okay? You can also say if the home directories are in /home, you can say /home can also be exported between other machines can access it. So the first step is you export whatever files you want other machines to access remotely. Okay? Now when this machine boots up, it can take any exported volume and set up a network mapping. Okay? This is called running the mount protocol. So let's say you have /, and then we have a directory called /remote. Okay, and then what you can do is you can say /courses is mapped here. And /home is mapped here. Okay. So this is done by setting up another configuration file which says go take this directory, /courses directory from this machine and make it accessible at this point in my local file in /remote. So if you do this, and when the machine boots up, if you simply cd into /remote/courses, you will actually now be accessing these files here. Okay, they look like local files, but they're actually files that are stored on the remote machine. Okay? Because what you've simply done is you have basically created a mapping saying this is the same as this, which means when you try to access this, you actually have to send that request over to the file server or you're accessing files here. Similarly, when you're accessing something /remote/home, you set up a mapping to /home here. Okay? Is that clear? Has anyone used it or configured NFS themselves or any Linux box? You have a question?
Yeah. So when you guys make this mount point, is the idea that the remote so the remote directory actually has a subdirectory called forces and home, and you just automatically map, or is the idea just the remote maps to both of those setup?
So what you will do in this case, you will create an empty directory called courses here. Okay. And you will simply say that whenever the user tries to access anything here, okay, that corresponds to that volume here. Okay. So this is an empty directory. That's an empty directory as well. In some cases, this directory is created for you on the fly, but that's a separate optimization. If the directory doesn't exist, it will be created on the fly, but it looks like a local directory except that it's empty. And all the files that reside within it are actually files that are stored here.
Could you have a combined system where like you have some local files on it, but also it's mapped to some?
Yeah, so you will have other files. So you have user, local, and so these are actual local files. Okay, so you have your local disk. Some directories in the local disk simply get mapped to remote directories. It's not that there are no files on my local machine here. There are the same files, but you treat some directories special, saying those are directories where I'm going to forward the request to a remote machine. Yes.
So do they just act like links?
I'm sorry?
Do they just act like links? Like you just click on it and...
Yeah, so they are not links per se, they look like that. It is just a convenience whereby everything here is simply forwarded to, anything in there is simply forwarded to the file server. Anything we need a request to access files in there are simply forwarded there. Okay, links are things you set up on local machines. Okay, so links like a soft link or a hard link just allows you to create what's called an alias. It's an aliasing mechanism where you can access another file or using a different name, just as in Windows your shortcuts and things like that. Okay? Slightly different concept, but a similar idea. Okay? So you basically have, so this is distributed computing, right? So you have a directory here, okay, that just looks like a local directory. And when you go in there, you are sending all the requests to access files. Every request is going here, okay, to the file server, and the file server is sending back responses. From a user's perspective, this just looks like you're accessing local disk, but it is not a local disk. Okay? Your question is?
Yeah, is it limited to just accessing
Right, so question, what is it limited? So once you set up this mapping, okay, there is no limitation. It just look, anything you can do on a local disk now you can do on the remote disk. Create directory file, create files, delete files. You of course need the right permissions. You can't just go and delete somebody else's files, but so long as you have permissions, you do whatever you could do on a local file. Okay? This is the same as you have home directory, right? If you log into the Ed Lab, you have a home directory. In most cases, the home directory was not on the machine you logged in. You could create folders in there, you could do whatever you want. Okay, just like you could do it on a local disk. Okay, the same thing is true here. So here is an example of a typical EdLab machine, and this is how the mappings are set up. Okay, so this is the configuration file that sets up those mapping at boot time. So this mechanism I was showing you here is actually in here. So you see /courses/CS300 on EdLab server 3, okay, is mapped to /courses/CS300 on my local disk. I have a directory called /courses/300, which is an empty directory. So if on that EdLab machine, I go into that directory, all requests are actually getting mapped to this remote directory on that server. Okay? So you will see that there are similar, so these are all home directories that are similarly mapped. So if there is a /users, users 4 volume on this EdLab server is mapped here. Okay? So this is basically how you set up, system administrator set up the mapping. When you machine boots up, those mappings actually are put in place. So now you can start accessing remote files. Okay, so this is referred to as NFS's mount protocol. Okay, mounting is the process of setting up these mappings. Okay, so you can basically go and set up these mappings. At boot time, you can also configure them after the machine has been set up. Okay, so we are, yes, sir.
Changing the name locally affect anything?
What's the question?
If you change the name of your directory on your local machine, is that?
So if you change this directory or some other directory in there, is that what you're asking?
Yeah.
Yeah, so once you make a mount point, that this volume just looks like a local disk volume. You can do whatever you want. You can go and delete directories, change the names and so on.
And then if that file has the mapping and you reboot it, will it still, so it'll change, it'll know, so it won't mess up your mapping?
So are you asking if on my local disk I delete this directory CS300, what will happen? Before mounting, is that the question?
Or if you change its name, like, to user, yeah, if you just change, what if you just change the name?
Yeah, you could change the name. You don't have to mount this here. You could have called this something else, /courses_foo, and it would then appear as /courses_foo. Okay, this correspondence doesn't need to be there. You can change the name. It will get mounted somewhere else. The users will need to know that that is where they need to go to access their files. Because you can change the configuration as a system
Change the
admin.
name, but you don't change that configuration.
Okay, so if you're asking the configuration doesn't change but the name is changed, then you'll get an error saying that I did not have a directory to mount. So first create that directory. Okay. Or you can have something called automount that will create directories for you on the fly. Okay, so you can have one of those two mechanisms. Okay, so this is called the mount protocol, and I can show an example if I can get it to work. Okay, so let me just see one. So this is a file server that I am looking at, and I'm going to look at the same file there, file system tab, and you will see that here is a mount configuration file. That is the file, the line I highlighted basically takes a server called ADA. There's a directory in there which is has a mat code for an application called MATLAB. And then you mount it as /export common MATLAB. Okay? That's the mount point for this. Okay, and then you can now, I'm going to show you what will happen if I cd into /exp /common /MATLAB. Okay, so I'll see some files in there. Okay. So now those files are actually files that are coming from a different file server because there is a mount point that has been created. And if you run the df command on any Linux machine, that tells you what file systems are mounted, and I'm just going to look for this one, and you will see that it actually mounted that file, and you can see what is its size and whatnot. So if you look at, so you'll see it has a 4 gig partition that is mounted, is 91% full and all of that. And then if I'm in that directory, so these are all remote files, so I can go into any file in there, so I can go into bin, and now these are also all remote files. All of this is actually coming from a different machine. They look like local files, okay, but they're all remote files you're accessing from a file server. Okay, so from a user standpoint, you often don't even know under the hood that the files are not remote. I could delete these files, I could create new files, new folders, whatever I wanted. Okay, so long as I have the permissions to do it. Okay, so that's an example. Now, what I just showed you was an example of how things work in the Unix and Linux world. Same concepts apply to Windows and Mac. Okay, you have to create either a network drive or a network volume, and then you can go into those folders and do whatever you want to do as if you are accessing local files. Okay, so that's NFS and mount. Okay, so this is just a picture that shows you whatever I showed you here. I'm going to skip over that. Okay, and then talk about some more advanced naming strategies of larger file systems such as Andrew and Sprite. Okay. So Windows, Mac, Linux, they all either use the concept of a network drive or the mount protocol to access files stored on some other servers. There are other file systems that have what is called a global namespace, which means you can access any file stored on any machine so long as that file has been made accessible for public viewing. Okay. So in this case, you have the notion of a global namespace, and you access files using a URL-like naming convention. Okay. Just as you use URLs to access web pages on any web server, and any web server that actually is accepting requests, you can go and access pages on that server. Okay. You can have file systems that do exactly the same thing. Okay. Other than accessing web pages or a web server, you access files over a file system from the file system. And the naming convention looks very much like a URL, where you would do something like you will say CD, and then you could say something like file server dot. I'm just going to make up something. Let's pick some other. So you can just do this. So if you say CD and give a long name like this, which says slash, give the name of the file server, and then put a slash and give a full name on there. If you just CD and do a CD, if you use a file system like that, you will automatically set up a mount and you will be able to CD into that directory. So you can CD into any machines, any directory, anywhere in the world, so long as the users on that machine are willing to make their files publicly accessible. Otherwise, there is no security left. You can go and access whatever you want. So any volumes that are made publicly accessible, you can just CD in this fashion, just as you give a URL and you will be able to go access it. This is referred to as a global namespace. The naming convention is preset, is the file server, and then a path name, so it looks very much like a URL. Okay. So there are file systems that will do this. There are two examples here. There are both research prototypes, although one of them is now being commercialized. There's one called Andrew file system from Carnegie Mellon, and there's another one called the Sprite OS, which had a file system of its own from Berkeley. This was back in the late 80s, early 90s. Okay. Andrew was since commercialized. It was available as a product, and there are many universities that had actually used that to run on their file servers, and you could actually access files in this manner. So if you are collaborating on a programming project with some colleagues somewhere else, you didn't have to do anything special. You just had to make those files accessible, and they could just CD into your machine and start accessing the file. So it made sharing of files very easy. Okay, so that's global namespace. The advantages is, of course, it allows you to be sharing becomes very easy. The disadvantage is you have performance problems, and you may have some less flexibility in terms of who gets to access what, can you restrict it to certain users, not other users. So you have to be careful of how you actually set up this sharing. Okay, so those are all issues to consider when you have a global namespace. Okay. So with that, I'm going to move on from how to name files and access files to how the file system is actually built. Okay, how the file server is actually built. Okay. So as I said, there are two ways to implement this form of access. So let's say you have a workstation that's accessing files that are stored on a remote server. You CD into a directory where the files are removed. How are those files becoming accessible on that machine? Okay. What is the mechanism used by the underlying distributed file system? Okay. And as I said, there are two ways to do it. One is called remote service, and the other is caching oriented. And broadly speaking, it depends on whether the file system sends requests to where the data is or brings the files to where the requests are being made, as I said. Okay. So the two mechanisms are now, if I CD into this directory and try to open a file, let's say project1.java. Okay. If that is, so one method is any request I make on this machine, every read or write request to the file is actually sent to the server, and the server executes those requests for you. Okay. So this is called remote service. All of my read and write requests to a file are sent off to the server, and the server executes it on its local disk as if they were actually sent by local applications. This is one way by which you are going to implement remote file access. The other way to access the file is when I open a file here that's remote, I'm going to make a copy. Okay, I'm going to take the file here and I make a copy here. And then all subsequent accesses become local. Okay? And when I close the file, okay, if I made any modifications, those changes are sent back to the server. Saying I modified the file, here's the new version of the file. Okay? So this is called the upload-download model, or also called the caching-oriented model. Okay? So you will see that in the first technique, the requests are being sent to where the data is. The requests go to the file server, the data resides on the file server. Okay? In the second technique, data comes to where the requests are. You make a copy. Okay, so you have brought the data over. Now the data is local, and all the requests are now being made local. Okay, so you have these two fundamental ways to implement your file system. Either you bring the data to where the requests are being made, or send the request to where the data is. Then practically all file system will employ one method or the other. Some may actually employ a hybrid approach of having both. Okay? Is that clear what I just said? So now we are going to take a look at a little more detail. Okay, so let's we'll come back to remote service when we talk about NFS in a little more detail. And thing to keep in mind is that you can implement using the remote procedure calls, as you will see. But let's look at the caching oriented first, and then we'll come back to remote service. So in a caching oriented model, what happens is whenever you open a remote file, you're going to make a copy from the server, you bring the file over, okay? Then you access the file remotely, or rather locally. And then when you close the file, you send back changes. So that raises a number of questions saying, are you going to bring the entire file over or pieces of it? Okay? If the file is 1 kilobyte, you can bring the whole file over. What if the file is it's a DVD that you're streaming? Are you going to make a full copy first before you let the user open it, bring 4 gigabytes? Is that wasteful? So you have to decide how you're going to bring the data out. You can bring parts of the data from a file, some blocks of the file, you can bring all the blocks of the file. Depending on your caching policy, you may get different performance and cost trade-offs. Okay? So this is basically the issue of when and where the blocks are cached. Okay? Second big issue that you have when you have caching is, what if I modify the file? I am a user, I modify the file, and another user accesses the same file from a different machine. What happens then? Okay. So this can raise a scenario where some users see old versions of the file when other users have modified the file. This problem is referred to as problem of consistency. Okay, and I'm going to show an example here. We can do some of this. Okay, so we have our file server here. Okay, so we have So you have files that stored in some directory here. Let's say you have client 1. The client 1 has a editor, and you open this file for viewing. Okay, so this file, then basically make a copy of this file. Okay, so this is it. You make a copy and you're going to access that copy locally. Okay. So your browser is going to display code from the file and you're modifying this file. Okay. Let's say now there's another client machine, okay, that is going to open the same file. Okay, so perhaps the same user or some other user goes and opens the same file in an editor. Okay. Now what's going to happen is, if you follow the same principle, you'll make another copy. Okay. So now you have a master copy on the server. You made a copy of the file on this machine. You made a copy of the file on this machine. And that client accesses its local copy. This client accesses its local copy. Now consider a scenario where the users are making changes to the file. So now what's going to happen? Okay, so the first user makes some change. Okay. The change is actually being made to the local copy. Okay. This user doesn't know about the change. Okay. They are still working with an old version of the file. File is now out of date because it actually has been modified. Okay. So the second user doesn't know anything about the change. Okay. So now you start seeing users or applications start seeing old versions of the file because of this mod. Okay. If you don't deal with this problem, you are going to have inconsistencies in file accesses. Some users see old version even though the file has been modified. Okay. Worse, you can actually trample on each other's changes. So let's say this user has made some modifications and so has this user, and neither has seen each other's changes. Okay. So when user 1 closes the file in their editor, the OS is going to say file has been modified and send it over. Okay. So now you commit your changes to the server. Okay. Now user 2 eventually closes their editor, okay, and they will send over their changes and override the first set of changes. Okay, so now you basically deleted some modifications made by one user. Okay, because you simply overwrote the file and a new version that you sent to the server. Okay, so you can have all sorts of problems of this type if you do not deal with this issue. Okay. Now if you had the first model, you would not have this case at all. Because what would have happened is you don't make copies in the first model. Okay. There's only one copy, which is the master copy, which always resides here. So whenever this editor makes read and write calls, those read and write calls are shipped over a network, and you're actually reading or writing data here. And when you read or write, you're also doing the same thing. So when you make a write, those writes are immediately sent to the master copy. There's only one copy, which is on the server. So when you open the browser here, you will actually see the same changes. So all changes are immediately sent. There's only one copy, so you will not have scenarios where you have inconsistency. Okay. Whenever you have multiple copies of a data, if one copy is changed, unless you have something extra to make sure the other copies are updated, your other copies become stale. Okay. This is a standard problem in any distributed file system. You're just encountering it in the context of a file system. Okay. But it's a fundamental observation. You make multiple copies, you change one but not the others. The others are out of it. Okay, so you will always, when you have a scenario like this, you always have to extra mechanisms that send the changes to all other copies. Okay, this is referred to as you're maintaining consistency of your data. Your data should not be inconsistent. Copies shouldn't be inconsistent with one another. Okay. So this is essentially these two bullets here, saying what is going to happen when you make changes, how do the changes get sent back, and so on. Okay, so now the other issue there that's being mentioned here is when you make a copy, where does the copy reside? Okay, I did not say that. You can have one of two choices. You can make copies in memory or you can make copies on your local disk. Okay? If you make a copy in memory, if your machine crashes, all of your changes are lost. Any changes that are not sent back to the server will disappear because memory is volatile. Okay? If you keep the copy on your local disk, it's a disk cache as opposed to a memory cache, then even if your machine reboots, the disk cache has not gone away, you can still take the old changes and send them, old updates and send them back to the server. Okay, so you can keep your cache either on disk or you can keep it in memory, and depending on which of the two you use, you will actually have different trade-offs in terms of whether you lose data when the machine boots or not. Okay. So the other thing that you have when you have caching is this issue of write through and write back, which we had encountered not too long ago. Yeah, it's like whenever you have caching, you can have one of two policies. You can have write through caching or write back caching. Okay? Same is true in a file system as well, because this is essentially a cache whenever you're making a copy. Okay, write through caching. First, let me ask, do you remember write through and write back? So write through essentially says whenever you make a write to your copy, okay, you send those changes immediately to the master copy. Your writes are actually going through the cache and hitting the master copy. Okay. Write back essentially says whenever you make changes, you only modify the local copy and send the changes to the primary at a later time. Okay. The scenario I was showing you here, okay, assume that you had used write back caching because the editors were making local changes. The changes were not immediately sent to the server. Okay? That's called write back. If you employ write through, whenever you make an update to your file in the editor, those changes would have to be sent back. That's the definition of write through. Any update to a copy is immediately sent off to the server, to the master copy of the server. So even in a distributed file system, you have the same two options. Okay, and this is fundamentally a performance and reliability trade-off and a consistency trade-off. Okay. Write through is always slower because every update to your local copy has to be sent to the remote server. Okay, that's going to take extra overhead. Okay. Write back gives you better reliability and better consistency because all local changes are sent to the server, so the master copy is always up to date in write through. Okay, so you have the same true trade-offs that you have to deal with here. Okay, whether changes to your cache are sent over or not sent over. And the third issue is that of consistency, which I already mentioned, which is how are you going to keep these two copies in sync when there are changes made. Okay, so let's talk a little bit about that. So the scenario, the example scenario here is you have a master copy on the server, two copies on the client. Okay? And one of those copies has been modified. So the question is, what should happen to keep the master copy up to date? How can you go about implementing this technique that will update the master copy? Okay, so the problem is clear. So we are talking about the problem of maintaining cache consistency. You have a primary copy of the file here, file1.cc. You have a cache here, okay? And there's a copy of the file here, and this cache is another cache here. Copy of the file in this cache. Okay? So now, if any of these copies have been modified, you have to eventually send the updates to the server. The question is, how would you go about doing this? So what would you implement to send those updates? How would you go about implementing a scheme to maintain consistency of your caches? Any ideas on what you could do? Yes. Okay. You could have a merge procedure. The merge is simply sending the updates over. Yes.
I was going to say before that you can compare checksums and then if they're different, you can take the files.
Okay. So you could also keep what are called checksums, which are essentially hashes of your file, and you could compare them, see if the file has been modified, and send those changes over. Okay. So you have to actually do all of these things. Okay. You have to track. So first thing is to implement cache consistency protocol within a cache. Anything you have cached, you have to check whether this has been modified or not. You have to track. Whenever anything in the cache is modified, you have to set that page or block or file to be dirty. Dirty means it has been modified. You send a dirty bit. Okay? Now that's the first thing you will do. The second thing you will do is you will basically have to decide what parts of their object are changed and when do you send them over. Okay? And what is shown here is you can implement cache consistency either at the server or the client, which means it's either the job of the server to ensure that the primary is up to date with cached copy, or if the client initiated is the job of the client. Right? So if your server initiated consistency, the server will periodically ask the client, saying, has your copy changed? And if the answer is yes, the client is required to send any update. The answer is no, you'll say no, nothing has been changed here. So periodically the server will poll its client saying, has the copy changed, and has the copy changed, has the copy changed, and that's how you will actually implement server initiated consistency. In client initiated consistency is the job of the client to not only send the updates but to keep checking with the server. So if you modify the server file here, you will send over the file at some point to the server. And then other clients still need to keep checking. You'd ask the server saying, has the master copy changed? Has anyone else changed it? If so, send me the new version. Okay, so you have to do both things. You have to send updates to the server, and then you have to keep polling the server to see has the file changed so that you have the latest version of the file. This is called client initiated consistency. Okay? Anywhere you have consistency, you will actually have to use one of these two models. Okay? So another example of caching is you have web browsers. Typically, web browsers have a cache. Okay? Whenever you access your web pages, there's a copy of whatever you have accessed actually stored on your local disk. In addition to cookies and everything else, the web browser also creates a cache. Okay? Now, if the page actually changes on the website, let's say you access the newspaper website, okay, which will change frequently. There will be new stories being posted and so on. If your web browser actually caches a copy, okay, and if it just, whenever you access the website next, if it just gives you the locally cached content, you are going to see an outdated version of the website. Okay? So it's the job of the website, web browser in this case, to check with the server to make sure the web page has not changed before you allow it to access the cached copy. That's client-initiated consistency. Okay? Typically, what your web browser will do, whether it's Chrome or Firefox or any other web browser, if it sees a cached copy, it will make a quick check with the server. Okay, by sending a special HTTP request saying, I downloaded this page at this time, has it changed? If it has changed, then you fetch the new version and display it to the user. If it hasn't changed, then you can just take whatever you had accessed last time and just show it in the browser. Okay, so that's how you will implement it in a browser. Yes, question?
If you have to make a check every time you open up a cache page, then how does that save? Aren't you not saving any time, or how does that save time?
Good question. The question is, if you have to check with the server every time you have to access this, does it save any time, or how does it do? There are two answers to it. One is it is faster to just check if a file has changed than to bring the whole file. If it's a big image or a large file, you are just making a request and you get a yes/no answer as opposed to downloading a larger file. That's one point. Okay? Second point you raised is actually true, which is even if I have to make a simple yes/no check, that still takes some overhead. Okay? So many browsers will not even do that. They will check once in a while. They won't check every time. So if you access the page 5 times in the next 3 minutes, they're not going to check. They may say, I'll check every 30 minutes. If it has been more than 30 minutes since I cached this copy, only then I will check. So in that case, you are actually at risk of seeing outdated content. Okay? File servers do the same thing. Many file servers in Unix use a 30-second window to do these checks or to send data out. So in that case, your data may be out of date by up to 30 seconds. So if you make a write, you save it, it may take 30 seconds for your client to send it off to the server. Okay? So if some other client accesses that, it in the 30-second window, it will see an outdated version of the file. Okay? And you do this only to prevent exactly what was pointed here. Is if you have to make a check every time, that's going to be high overhead. You can implement it, okay, but it will be higher overhead than saying I'm going to do it every 30 seconds or 30 minutes or some interval. Okay? But that interval is going to define what's called your cache consistency guarantee. The interval says any data you access can be out of date by at most that much period, whether it's 30 seconds or 30 minutes. Okay, or you can say, I check every time. In that case, there is never going to be auto. So you have to make this trade-off in your system. Are you going to pay the higher cost of doing checks every time? Are you going to leave an interval and say, I check every 30 seconds and whatnot? Okay. So all of these are very important questions that you have to answer when you implement any caching framework, including file system cache. But if you build a web browser, same questions come up. So you have a cache, you have to figure out whether data in your cache is correct. Yes.
We talk about these trade-offs a lot, and I wonder if there's a even bigger overhead to leaving that decision to the user. Like, if you can have a setting where you can change that.
So I think that's a good point. The point being made is, should the system bother or should you let the users decide on consistency? There are many applications where consistency is actually left to the user. Okay? There are many browsers that will not even do what I said, which is actually check with the server. If you find content in the cache, they'll simply load that content. Okay? And then if you actually do shift and say reload, it will actually go to the server. Okay? That's an explicit mechanism that's built into many browsers. They will not bother. It's a user can figure out if the page looks out of date, they can just do shift and then say just refresh, and it actually refreshes from the server rather than the cache. Right. For a file system, that doesn't quite work because there is no expose mechanism that says give it from the cache or give it from the server, because you're trying to ensure transparency. The user doesn't even know what's happening under the hood. In a web browser, where you actually know that the content is coming from a server. That's explicit to you. But in a file system, you are accessing files because you don't know whether a local file is not. So you actually have to do this within the OS. But as you point out, in many cases, you just let the user figure this out. So you just don't do anything at all. Which is somewhat convenient to write code, but the users have to deal with all of this problem. Right, so we will move on and talk about quickly about, because we're somewhat short on time, on case study on Sun's network file system. So we've talked about some concepts, which is how files are named, how files are accessed, if there is caching of data, how do you actually go about making sure the cached content is correct and so on. So now we will see how these concepts are all put together in a real distributed file system. And the case study is one of NFS. So NFS stands for Network File System. Okay? This is the default distributed file system that comes with all flavors of Unix and Linux. Okay? It's also supported on Mac and Windows. Okay? So it is a very widely used cross-platform network file system. The file system does not put any restrictions on type of client and type of server. Server can be running some flavor of Mac, the client can be Linux. Flavor of the client can be Windows, server can be some other OS. Okay, so there is no requirement that the client and the server run the same OS, they run on the same platform. So long as there is a server and it talks NFS, you can take data that's stored on the server and have it be accessed remotely from any other client that also has NFS capability. Okay, so it is a cross-platform file system. It is a fairly old concept now. It was designed back in the 80s. Okay, it's more than 30 years old. The file system, it's evolved over time, but the first versions of NFS date back to more than 30 years old. Okay? Originally, this was designed to run over LAN. Okay, this was designed as a way by which you could have one expensive machine on your network, which was the file server, which would have disks. In those days, disks were still expensive. Okay, so you would have a file server that had disks, and you would buy cheaper machines that were essentially diskless. They usually called it diskless workstation. They did not have a local disk at all. Okay? All they did is they actually ran NFS and accessed all of their data that was stored on the file server. This allowed you to buy more machines at a lower cost, because machines in those days were still expensive. Today, this model doesn't make any sense at all, because disks are so cheap, you can basically put a disk everywhere. So you use file server simply to keep data in one place, not to save money. Okay? And you have also cloud-based servers like Dropbox and Google Drive and all of those. Those are the same concept. They just extend file sharing over the internet. Okay? The protocols are now no longer at OS level. These protocols run over HTTP. Okay? You are accessing files over HTTP rather than accessing files over an operating system's RPC protocol, for example. Concepts are no different. Okay? Protocols have changed. Okay? And where the files are changed as well. Okay? So NFS was originally designed to run over LAN. Today it works over the internet as well. But if you are really trying to access files over the internet, you, as I said, you have better mechanisms to do it. Okay? You could use Dropbox or other means to do the same. Okay? In NFS, any machine can act as a server or a client or both. You can be a server for some of your local files. You can allow some of your local files to be accessed somewhere else. You can also be a client for data that's stored on other machines at the same time. So you don't have to be either a client or a server, you can be both. You can be a server for some files and a client for some other files. Okay? Now, there are two versions of NFS depending on what OS you use. Okay? NFS version 3 is by now somewhat outdated but still widely used. The new version of NFS is called NFS version 4. So this is the 4th generation of the NFS file system. And I'll say a little bit about file systems being stateful and stateless in a little bit, but for now I'm just going to say that until version 3, NFS was purely stateless. Starting version 4, it has become stateful. What this has got to do with anything, I'll come back to this. Let's talk a little bit about some other things like the mount protocol. Okay? So I already mentioned this notion of mount. Okay? This comes from the NFS world. This is where this concept actually came about. Okay? So the designers of NFS said, we don't want users to figure out they need to set up network drives and all of that. It should be transparent to users. They should just cd into some directory and start working on whatever files they have. Whether the files are local or remote shouldn't be a user's problem. Okay, let the system administrator do a one-time configuration setup, and whenever you boot up, you read that configuration file and you set up the mappings. Okay, and so users shouldn't have to deal with this. So let's make it easy for user. That was the philosophy. Okay? To do that, they came up with this notion of a mount protocol where the server has to specify through a configuration file called /etc/exports what directories are accessible remotely. Okay? Only those directories can be accessed. If you try to access some other file on that server, the server will give an error saying you are not allowed to access those other directories. So when you boot up, you decide these are the directories that I will let clients access. Okay? This could be home directories, your inbox, mail directories, and all of those directories. And on the client side, you have another configuration file called /xtfstab. This is called file system table. That is going to set up these mount mappings. That is going to say, go to this server, take this directory that it has exported, and make it accessible at this point in my local file system. Okay? So certain directories in your local file system simply become forwarding directories to actual files that are stored on a remote file system. Okay? So when you cd into those directories, because of this mapping, you will start accessing remote files. So that was basically the way the mount protocol works, and we looked at examples of that already. Okay. So these are the two configuration files you need to maintain, one on the server side, one on the client side. If you have both a client and a server, you will have both of those files on your machine. So even Macs that support NFS, so if you have access to a Mac, if you go and look at these files, you'll see that some of them might have entries if they are configured by some application or the other. Okay, but if you haven't used NFS on your machine, these files will be empty in most cases. Okay. Now, as far as implementation of NFS goes, NFS is implemented completely using remote procedure calls. Okay. In fact, NFS was the first applications that extensively used RPCs. Okay. Back in the late 80s when NFS was being built, RPCs were also a new concept. Okay. So the designers of NFS said, here's a nice way for us to implement use remote procedure calls. Whenever you make a read or a write, okay, and if there are reads or writes to remote files, we just make reads or write within the OS as RPCs, and one OS is going to make RPC requests to another OS. So I'm simply going to say make a read request, and that read request will be an RPC that go to the server. The server will then treat it as if it's a local read request. It will execute it and send back replies. Okay, so all of your file I/O calls become RPC calls to a remote server within the NFS one. Okay, so that is how the designers of NFS used RPC. It was the very first application of RPCs in the commercial setting. Okay? And after they built NFS, they decided this is a technique that is useful way beyond just writing a distributed file system. So they built an RPC compiler, and now any user, any application writer can use it for their application. So they actually took the RPC implementation from NFS, they spun it out into their own set of tools, and now you can actually use it for all of your applications as well. Okay? But RPCs were actually put in place within the Unix world for the very first time when NFS was being made. This sort of a history of how RPCs and NFS all sort of share some of their heritage. Okay? So that's basically how you implement it. And as I said, what is going to happen is whenever your client is going to make any request, read, write, open files, and so on, your system here is going to simply send RPC request to another machine. Okay, that machine is going to service those requests, send back replies. Okay. All of this RPC implementation is actually in the OS. Okay. This is not an application. So here is an example implementation of NFS inside the kernel. Okay. So this is a part of the file system inside a kernel. And this kernel supports two file systems. This is your local file system that accesses local disk, and this is NFS. The way this works within your kernel is there is something called the VFS layer, okay? The virtual file system layer. That's a wrapper that sits on top of both of these file systems. Okay? So when applications that sit on top make read or write requests, first it comes to the virtual file system layer within the kernel. The virtual file system simply looks at the read and write or open whatever I/O request you're making and says, is this going to a local disk or is it going to a remote disk? Okay? So you think of it as a big if statement. So your virtual file system is simply checking, is this request going to a local disk? If so, it forwards that to this part of the kernel code. If it's going remote, it sends it to this part of the kernel code, which implements NFS. Okay? So if it comes here, then you do the same thing what we discussed. It goes to the device driver sends it to a disk and so on. Okay? That's your local file system and local disk. If it comes here, then this NFS code here actually implements RPCs. It is going to say, if it's read, it's going to make a read request. That's an RPC call that's going to go over the network to a server. The server will receive that RPC call, will actually read your data from the local disk and then send back the response. Okay? And then the response is going to come back here and to send it back to the application. As far as the application is concerned, this is completely transparent. Okay, you are simply making a read or write request without specifying is it local, remote. All of that is actually being done inside the OS through this virtual file system mechanism. It's called a VFS switch. Okay, it's a big switch statement. Okay, you can use the same mechanism to support other file systems as well. This is an example of just having two. But anytime you add support for a new file system, you do the same thing. Yes, and that VFS layer, whenever a request comes, decide, is it going to be handled by UFS? Should I send it to ext3? Should I send it to my FAT file system module because it's a USB drive or whatever else it might be, and you will forward it to the right file system module inside the kernel. Okay, this is an example of just distinguishing between local and remote files, but you can also distinguish between file systems using the same mechanism. Okay. So that's a good picture to keep in mind, because it tells you how local and remote files are handled, and when your remote files, how RPC is actually used to access data from a remote file system. Okay, so I think we have run out of time, so I'm going to just stop here. There are a couple of slides remaining. We'll come back to that next time.